Namaskar my dear friends. Let us talk about the PWM controller. We have already seen several PWM controller like UCC28 series, let's say 4x series or C5x series. Similar to that we have 38C4x series and 38C5x series. So there are a lot of variants of UCC series, and one of the very popular series for PWM controller to design all switch mode power supplies and all. In this session what we'll try to understand is we'll take up one IC which is UCC27517, and this is a single channel, like it can drive one MOSFET, and it is very high speed with low side gate driver, and it can give you pulse current up to plus minus 4 amperes. So basically this particular IC is much more simpler compared to UCC28 and 38 series. They were having 6 pins, and this is having 5 pin itself. Okay, so 5 pin is more than enough to drive. They were actually, I think, more than 6 pin. I think 10 pin or 8 pin was there. Anyway, the thing is, this particular PWM controller which we are going to see is going to have UCC27517, and this can be utilized in your switch mode power supply design, let's say AC to DC converters and all. We have DC-DC converter requirements where basically, you know, like transformer coupled DC-DC converters we basically use. We have gate driver devices for digital power controllers. We have solar power, motor controls, and UPS. We have gate driver for emerging, you know, like wide band gap power devices, let's say GAN based devices. So what is this particular device? We can see very quickly that this is particular device which is going to be UCC 27516 and 17. So the both of the devices will be having same concept almost, and this can drive your MOSFET as well as IGBT both. Okay, before moving to the complete description about this particular device, what we can do is we can understand what is simple SMPS block design that we do basically. So let us say we have AC signal input here which will be around 85 volt AC to, let's say, 265 volt AC. And what happens, basically we utilize some fuse, some safety features, let us say MOVs, and you know, like we try to use X capacitor, Y capacitor, and common mode filters or something like that. Then we send this signal to, then we send this a particular power line to bridge rectifier, and this rectified output goes to transformer. There are a lot of circuits in between, like snubber circuit and bulk capacitor, all those things will be there. However, our main aim is to drive this particular transformer in its switching form, right? So for that purpose we will be using one high current MOSFET whose you know, like this is kind of drain, this is my gate, and this is my source. So this drain will get sorted to source, and this is how the transformer will get charged, and it will send the signal to secondary side, right? So for this switching purpose we try to utilize PWM controller. So this is the device that will be our UCC27517. Okay, and you will get your, after filter and capacitors, you will get your V output. So this is my output voltage. Let us say we are going to set it to 15 volt or something like that, and then to regulate this particular voltage we design some voltage divider or some V reference ICs. Okay, let's say TL431 or something like that, or a simple resistor divider will also do, and this one we send it to our feedback. So this feedback can be sent through a feedback isolator, maybe optocoupler or something, if you want to have isolated DC-DC converter or AC-DC converter. If you do not want, like if you want non-isolated, then there is no need of optocoupler. You can directly send it to the PWM controller if it is required. And to drive this PWM controller we need a PWM signal that can be taken from the controller, which will be our microcontroller, right? So this is the basic building block of our SMPS design that we have in our hand. Let us now understand what is the features and application of this particular device which we are discussing, which is UCC27517 and as well as 16 both. So what is going to happen is it is very low cost. That's the biggest feature. Okay, so in this particular competitive market we have to have utilization in automotives and as well as industrial and consumer applications. So there, this is going to be very low cost, let's say around $0.2 or something per 1,000 pieces. That is actually booklet price. It can be even lesser for little bit higher quantities. And it has very fast propagation delay, so that is the biggest thing. And it has supply voltage range up to 4.5 volt to 18 volt, so it is very much suitable for your 12 volt application or 15 volt application. Even 9 volt application will be very good. It has the compatibility of TTL and CMOS both, so either you can have 5 volt logic or 3.3 volt logic, both will be suitable for this particular device. So the PWM signal that you will be using can have a logic levels of 5 volt as well as 3.3 volt, so it is compatible to both the logic level of TTL as well as CMOS. So that's all. And it has a dual input like design, so it can work with non-inverting input, which will be input plus, and another one will be non-inverting input, which will be input minus. Okay, so we'll tell you while designing the circuit how input plus and input minus can be utilized. And it has two packages. One is 5-pin package, which is going to be SOT23 package. Another one is 6-pin DRS package, which is going to be WSON package. So if you want to have very small package, then you can go ahead with a WSON package. A little bit bigger package will be SOT package. We have already discussed about the applications, so we can move to the simplified application circuit. Okay, so if you see simplified application circuit, let us say we have 12 volt input to this particular device, that is my supply voltage. So only one capacitor will be needed. Let us say we put it 47 microfarad capacitor. One more capacitor you can add it 0.1 microfarad for the filtering purpose. That is a good idea. Okay, now this is my ground pin. This is the pin which is going to drive the like output MOSFET. So this is how it will work. So this is my PWM signal, let us say 1 kilohertz or whatever like designed frequency of signal that we can put it here, and the same signal will be coming out with a higher amount of current to drive this particular MOSFET. So that is the understanding, right? So let us say this is my MOSFET, this is my transformer which is going to get driven, and this will be like, let's say flyback converter or something like that, and it can drive it. So this is how it will be working very properly. So our main aim is to make sure that this particular transformer switches on, switches off based on the switching condition of this particular MOSFET Q1, and this is our main purpose. The another part that you can see is input minus is there. So whenever you are working with input plus, input minus must be grounded. Okay, if you keep it floating or if you keep it high, then it will be disabled, like output will always be low, it will never be high. So you can utilize this input minus pin as a enable signal also. So whenever you don't have to utilize this particular device, you can pull it up so that it will be not working, and whenever it is has to work, then you can pull it down, that is ground it. Okay, so that was one thing. Another simplified application can be based on this input, like inverting input, right? So all other parameters are same, you can keep it with capacitors and all everything. The only change that will come is PWM signal will be given to the inverting input. So inverting type will be, and at the same time non-inverting input must be pulled up to make this particular device work. Okay, so it must not be grounded. So this particular input plus can also be used as enable disable signal for this particular device by making sure that pull it down, like ground it, and otherwise pull it up. So this is how you can make sure that this is working. So how you can design that particular circuit? So what we can do is, let us say we remove this particular connection and we ground it permanently, right? And then take this particular signal and connect it to my MCU IO. Okay, so this is how it can work out. Understood? So I'll just tell you how it will work out. So whenever, let us say this is my 10K or something. Now how it will work out is, whenever this particular IC has to work, you can send a high signal. Okay, so once you send it high, this particular input plus will be pulled up and it will be working, and whenever you pull it low, so it is anyway grounded, so it is not working. Understood? So this is how you can design the circuit. Same way, if you want, you can design the circuit for this particular application also. Let us say disconnect this particular signal and you pull it high, let's say 3V3. So it is not working. Let's say we'll put it to 10K and then connect it to your MCU IO signal. Now whenever you have to make sure that this particular device to work, then in that case what you will do, you will pull it low. So when you have to, anyway it is pulled up, now you have to pull low, so to make it work. So the microcontroller signal will be sending a signal low so that this particular device starts working. Alright, now we can move to the next device. So before moving to the next part of this circuit explanation, what I have is, I have another device which is suitable for your automotive application. So it is same device UCC27517, but it is going to have A-Q1. So A-Q1 will be having a automotive application also. So there are various automotive application like you can have power supplies design from battery to like drive for various applications. So in that cases the same kind of circuit will be utilized for your automotive application as well. So you can see the typical circuit size exactly same, just now I have explained you, right? This is with non-inverting input and this is with inverting input. So this session is going to be applicable for both the circuits. One will be UCC27517 as well as automotive version, which is A-Q1. Now let us talk about product family that is there with UCC 275 series. So that can be have 16, then we have 11, 16, 17, 18 and 19. So there are like around 6 devices are there, and you can see some of the devices are having capability of 4 ampere and 8 ampere, and some of them are having 4 ampere capabilities. Okay, so our main concern is to use this one, which is going to be UCC 27517, as well as if you want you can go ahead with 16 also. So these two devices are our main focus for this particular session. Now let us get into the pin description. So what we can see is we have this SOT package, SOT23 package of 5 pin. So you can see we have VDD pin, we have ground pin, we have input plus and input minus, and we have output pin. So this is going to drive my MOSFET like this. This will be my gate, drain and source. Understood? So this is very simple design. There is no feedback requirement, there is no current sensing like requirement. All those things are taken care, or all those things are not needed. This is very simple design with very low pin count numbers, and this is going to be 27516 with 6 pins. Okay, so if you see in 6 pin you have 2 grounds, that's all. That is the only change that you can see. This has only 1 ground, this has 2 grounds. So pin configuration, if you can see, input minus, so input minus you have to give inverting input. So when the driver is used in non-inverting configuration, then input minus must be connected to ground. That was the thing that I have just now explained you in your typical application. Okay, similar to that we have ground, we have supply voltage, we have output. Now coming back to the input plus. So input plus, this is non-inverting input. Now when the driver is used in inverting configuration, so this is my inverting configuration, then we must connect this input plus to the VDD. Okay, otherwise what will happen? Output will be low if input plus is unbiased or floating. So if it is unbiased or floating, like you do not connect anything, then it will output will not come. Similar to that, if you do not connect to input minus when it is working in non-inverting configuration, then also it will not work. So you have to make sure these 2 pins should not be left out if it is working in inverting mode or non-inverting mode. Okay, so similar to that you have UCC27517 device that is having only 1 ground. So you can see we have 5 pin, and the functionality is all actually same, exactly same, whatever just now we explained for the 6 pin device. Let's get back into the absolute maximum rating. So if you see absolute maximum rating, supply voltage it can take up to 20 volt. Then if you are giving more than 20 volt to the supply pin, then it will go bad, like it may get damaged. So you have to make sure that supply voltage does not exceed 20 volt to the VDD pin. You can see output stage is going to be VDD plus 0.3. So these are all like a maximum rating that is there. Output continuous current, if you want, you can have 300 milliamperes, that is 0.3 amperes, and pulse current whose the width will be less than 0.5 microsecond. Okay, that is the thing that you have to understand. So the peak current will be there, but this width must be less than 0.5 microsecond, then it can give you up to 4 amperes of current. Now let's get into the other part, which is going to be my recommended rating. So before that we have ESD rating, which is a human body model rating, which is going to be 4 kilovolt, that is 4000 volt, and that charge device model, that is CDM model, is going to have plus minus 1000 volt. If you talk about recommended operations, so recommended, the supply voltage must be lying between 4.5 volt to 18 volt. So nominally it will be used 12 volt. So 12 volt application we have anyway used, several application we have designed, and we have utilized this particular IC. You can see operating temperature range is up to 140 degree centigrade, and lower side it is minus 40 degree centigrade. This input voltage on inverting input and non-inverting input both can take up to 18 volts, so that is not a problem. But anyway, we will be giving logic supply. So logic supply, if you are giving 5 volt or something like that, then you can give it. Otherwise what happens is, sometimes my gate requires little bit higher voltage. In that case, you can supply input plus and input minus to a translated voltage to little bit higher voltage. Let us say 10 volt or something like that you can supply, and it will not go bad. If you can see junction to ambient thermal resistance, so we have thermal information also. So in WS1 package it is just 85.6 degree centigrade per watt of power dissipation, and similar to that SOT package is going to have 270 degree centigrade per watt of power dissipation. If you talk about little bit more electrical characteristics, so VDD, if I take the condition of VDD as 12 volt, then what will happen is, under voltage lockout you have to make sure that my switching on will happen only after 4.5 volt. Okay, so below that it will not switch on, and while switching off it will switch off at 3.7 volt. So what happens basically is, let us say it starts like this, so it reaches 4.5, then only it will start switching on, and then it will start go to 12 volt. But once it starts switching off, then it will go little down and then it will switch off. So this will be 3.7 volt. Understood? So this will be 3.7 volt, this will be 4.5 volt. So this is how the switching action will happen. The output will be considered as high whenever my voltage is more than 2.4 volt, otherwise it will not consider it high. So threshold high is 2.4 volt or higher, and threshold low is less than 1 volt. So you have to make sure the PWM that is going into your input plus input minus must be lower than 1.0 volt and higher than 2.4 volt. So anyway, any logic that you are going to give for your PWM, that will be definitely 0 to 3.3 or 0 to 5 volt or 0 to 10 volt, whatever it is, but it should not be more than 1 and less than 2.4, otherwise it will not know what is the signal, whether it is high or it is low. Okay, and the sourcing and sync capability is plus minus 4 ampere. Let's get into the detailed description of this particular device. So as I already told you, this UCC27517 or 16 is a single channel high speed low side gate driver device, and can effectively drive a MOSFET as well as an IGBT. Okay, so IGBT also one MOSFET, both it can drive, and it is a low side gate driver, that you have to make sure, and this is a very high speed single channel device. So anyway, this we already know. Now let's get into the benefits that we are going to get from this particular UCC275 series. So as you can see, we have a very good source or sync capabilities of this particular device. So up to plus minus 4 amperes, that is one thing. It is having extremely low pulse transmission distortion, so there is no distortion because of very low delay. It has very good flexibility of VDD supply range, so you can see expanded VDD operating range from 4.5 volt to 18 volt, and it can also be used in GAN devices. Okay, now it has under voltage lockout protection, so it will not overload the system or the output, so that's the advantage. It has output held low when input X is floating condition, so that is going to save your device. If one of the input is floating or not connected, it means it will be having a safety features of not giving you the output at the MOSFET gate, right? So this is how some more benefits are there. It is nothing to worry about. It has a Miller turn on event as well, so you have to have high immunity because of C into dV by dt. So that is going to have an like while switching off, what happens is, this is my drain, this is my source, and this is my gate. So in the previous session I have told you already, while switching off, the drain like has to discharge. So this particular like device has turn on switching Miller turn on event. In that case it will take that path to like get discharged. Let's talk about block diagram of this particular device. So if you see the block diagram, we have input plus device, which is going to go with a pull down device, a pull down resistor, and this is our buffer. It is having hysteresis type buffer, like with some hysteresis, like it can be considered as ischemic trigger type. So it does not give you like unwanted signal just based on the output, high or low immediately. So this is a very good feature here. Similar to that, input minus also is pulled up, and it is also having the ischemic trigger type buffer. Now it is going to all go through the AND gate, and then it is going through this particular amplifier to drive the output. So it is going to give you the output signal as and when it is needed. And this is my supply voltage pin, which is going to supply like give the supply for the internal circuitry. Similar to that, we have under voltage lockout feature through this particular VDD only, and all these signals, all these three are met, then only the output will happen. It means any of these 1, 2 and 3, any of these three signals are not meeting the condition. This is a AND gate, so it will be 0. It means output will not appear. So that's the reason it was telling you that when if you are working with input plus condition like PWM signal, then this must be grounded. Okay, so this is how, if it is grounded, it means it will see 0, and this is a NOT gate, so this will become 1. So when it is 1, then it will be 1, 1, and this under voltage lockout is also 1 now, because it has met the conditions. So all these three 1, 1, it is going to give you 1 and this is how you will get your output high. And let's say these two are 1, 1, now your PWM is going low, so it will become 0. So that 0 will make it 0, so output will be 0. So only this will decide the output based on its condition, whether it is high or low. Similar thing can be taken for 27517 also. Exactly same like circuit is there, so you don't have to think of much. Let us get the power up sequence. So power up sequence, there are two conditions. One is non-inverting drive, one is inverting drive. So in non-inverting drive, what you can see is, let's talk about this. So let us say in non-inverting drive we have input minus as grounded. Now this is the output signal that will come up, right, at the MOSFET. You can see, let us say this is my MOSFET that is going to be driven, right? This is my gate. So this is the output signal that will go to drive the gate, right? So what will happen is, as my input power supply is meeting the condition of threshold voltage, my PWM going to the non-inverting input, okay, is, as soon as it goes high, it will take little bit of delay, right? So up to this threshold voltage, and then it will start getting charged, right? So you can see the output has started ramping up, okay, but it has not become stable. It went to second like a pulse, and second pulse also it has tried ramping up, and then in third pulse it has become stable, okay. So it will take 3 pulses to get stabilized. Similar to that, in inverting drive, it is having the same thing. As soon as my power supply goes beyond the threshold, what happens, my input plus will be held high, and input minus is going to have the PWM signal, right? And this input minus, which is inverting mode drive, so that goes low. At that time only you will be having high. Understood? So this also will take 3 pulses almost to get like a stable condition, and whenever this goes low, then only you will be having high, that you make sure, okay. That was actually shown very easily in your block diagram. Now let's get into the gate driver output structure, okay. So this is the complete circuit that we have. Let us say this is the complete circuit that we have of your UCC27517 device, okay. So what happens is, We have the input signal which is going to come up as PWM signal, that is going to come up with all this pull up and pull down, and this is working in a totem pole condition. You can see R high, R low is there, like ROH high, ROH low is there. These two devices, let us say Q1 and Q2, and these two devices are working in a push pull mode, and this push pull mode is going to give you the output signal to drive your external MOSFET. Okay. So this is the main structure of your gate driver output structure. Now, as we have already talked about, like input minus, input plus are there, which is going to give you the like drive output signal. So what is the device logic level that it works? So let us say I am going to work with input plus signal. So in that case, my input minus must be grounded. Okay, that is the thing. So let us say we are working with this. In that case, I have to see it should be low in both the cases, then only my signal will be high or low. So first case, let us say input plus is low, then output is low. Similar to that, when it is high, then output is high. So it has to be held low, and then only my signal is high or low. Based on that, output is high or low. Now coming back to another mode, let us say I am going to work with input minus signal, and in that case input plus will be pulled up, right? Let us say connected to VDD. So in that case, what will happen? My input plus must be seen high all the time. It means I have to see these two conditions, and in that case, in these two conditions, you see whenever it is low, then my output is available. Whenever it is high, then output is not available, it is low. Understood? So there are two tables that is there in this. In all other cases, my output will always be held low. So you can utilize input plus and input minus, one of them as enable disable signal also. If we talk about typical application, just now we have explained very clearly like what was the typical application for inverting mode and non-inverting mode. Okay, and similar to that, let us say what it says basically is input minus is grounded to enable the output. So you can see input minus is grounded and input plus is actually working. Similar to that here also, in non-inverting mode you can see for 5-pin configuration and 6-pin configuration, and similar to same typical application is there for like inverting mode input. So inverting mode input will be taking the like PWM signal, and output will be coming. So we have already discussed about this. Now what is the design requirement that you need to set while designing this particular circuit using this particular device? So first of all, you have to decide whether the input to output logic is non-inverting or inverting logic. Okay, so whether it is IN plus will be taking the input or IN minus will be taking the PWM input. Okay, so that will be the first decision. Next decision is input threshold type, whether it is a logic level or like what logic level it is, whether it is TTL or CMOS, what logic level it is. Now what is a bias supply voltage? So you can give bias supply voltage, let us say 12 volt or 13 volt, that you can give it. Okay, what is the peak source and sink current? So that can be minimum like 3 amperes you have to decide, otherwise it may fail. So you don't go ahead with maximum 4 amperes of current, decide up to around 3 ampere is maximum. Enable disable function, if you need, then you can utilize one of the pin as enable disable function. Okay, another pin will be taking the PWM signal. So if you are working with non-inverting, then input minus will be acting as a enable disable function, or otherwise you can permanently ground it so that the device is always enabled. And propagation delay must be less than 40 nanosecond, that you have to make sure. Moving to the last phase of this particular design, so what we need to understand is we need to understand the layout guidelines. So let us say we want to design the device with UCC27517. So this is 6-pin device WS1 package. So you can see WS1 package, this is the particular device which is U1, input minus, that is pin 1, 2, 3, 4, 5, 6. Okay, so this is the device. So this VDD pin is connected with like capacitor, you can see here, and the output pin is going to go here with one resistor like gate resistor, and this gate resistor is going to the gate of this MOSFET. So this is the Q1 which is my MOSFET. So gate is there, then this is my drain and this is my source. So drain will be taking the power from transformer, right? Like transformer pin will second pin will be connected to this particular drain. Let us say this is my drain, this is my gate, and this is my source. and drain to source will get switched on, and this source is going to come back to the ground of this particular device. So you can see two ground is there. We have one more input minus, so that is actually grounded because it is working in, let us say, input plus mode, right? So input plus is taking PWM signal here, which is coming from a microcontroller maybe. Okay, so this is how it can be have a proper layout, PCB layout, for better understanding. Your aim should be put another put additional capacitors at VDD signal, so you can have parallel capacitors, one or two more. Okay, that's not a problem. Whatever I discussed just now, you can have that way. For 5 pin, this was 6 pin. For 5 pin PCB, let us say this is my SOT23 package, 23 package of 5 pin. So in that case, you can see this is the device that we have. So we have VDD like pin number 1, 2, 3, 4, 4 and 5. So this is my output signal. So what is going to happen? This basically VDD pin is connected with our capacitor, like bulk capacitor that you will be having, which will support you for removing the transients at the input supply. And this is my return pin, which is going to be ground, right? Now coming back to this particular PWM signal, which will be fed to my input plus signal. Okay, so input plus signal is taking the PWM, and then it is going to give you the output drive to drive through this particular gate resistor. So there is a resistor between the gate of the MOSFET. This is the MOSFET that we are going to drive. Okay, so what is happening through this particular path? It is going to drive this gate. So this is my gate of the external MOSFET, this is my drain, and this is my source. And this drain will take the voltage from your transformer, and this transformer will be switched on by sorting this drain to source, and this is how it is going to return to the ground. So this is the particular thing that you have to understand. Now you have to have a proper meshing and proper heat dissipation. For that you have to have a copper exposed areas for the power dissipation. Okay, so hope you have a very good understanding about this particular device that we have just now discussed about this particular PWM controller. This is just 5 pin device. Okay, and you have to have just supply pin, and one driver signal will be there, and directly one output will come up. There is no other signal much that is needed. One ground is there and one input minus is there, which can be either grounded or either can be utilized as your enable disable signal. Okay, so if you do have any questions regarding this particular PWM controller for any of the applications that you want to develop it for low cost applications, you please put down your questions in the comment box, or do reach to us for any particular design that you are seeking to have support or guidance that is required for any of the applications in either industrial applications or consumer applications or maybe automotive application. Okay, or let's say there are some solar panels or motor control or UPS designs. In that cases also, this particular PWM is going to be very helpful to give you a particular set of output voltage that you are seeking in your board. So thank you so much guys. Bye.